They lie hidden beneath our feet, invisible for centuries. We never even knew they existed. Yet now, they shape our future, offering staggering possibilities, and at the same time threatening to devastate our environment. If you look at the periodic table, you'll notice two rows that seem to be kicked out or misplaced near the bottom. These are the rare earth elements, often ignored because they don't fit neatly into the main structure. Scientists started focusing on them because they boast several highly appealing technological properties. They may appear unremarkable, but they bind together like glue, making them difficult to separate. I see them as catalysts for future innovations in the 21st century. No real progress will happen without them. In this field, the hope for a better tomorrow quietly simmers. For a long time, these chemical elements were deemed useless because their properties were too unusual. Only recently did researchers uncover their true value, triggering a technological revolution. Today, they're more precious than oil or gold, the rare earth metals. We call them rare, not because they scarcely exist in nature, but because they're notoriously difficult to isolate chemically. Yet once purified, they grant us cutting-edge technologies, from smartphones and tablets to hybrid and electric vehicles. All our modern devices contain rare earths. Bio2, China, the world's largest rare earth mine. 97% of the global rare earth supply is mined in China. Excluding promethium, which is exceedingly scarce, all the other rare earth elements are found there. When rare earths are mentioned, people automatically think of China's enormous resources. The open-pit mine at Bao2, sometimes known as Bayan Obo, is technically an iron ore mine. Production began in 1927, and for decades, these rare earth elements were tossed aside as waste, until prices soared on the global market. A few decades ago, the Chinese discovered that the material lying atop iron ore in Inner Mongolia was actually rare earth ore. From the discarded overburden, they began extracting unseparated rare earth oxides. It might seem that China rose to world dominance by mere coincidence, but not everyone agrees. The president of the Chinese Society for Rare Earths notes that, starting in the 1950s, China began surveying rare earth deposits and set up processing systems in the 60s. By the 80s and 90s, large-scale production was in full swing. Today, the entire world depends on these metals, dug up in China using outdated, polluting methods, then sold to high-tech manufacturers for smartphones, electric cars, and wind turbines. Matthias Buchert, from the Institute for Applied Ecology in Darmstadt, knows how hard it is to produce rare earth elements. They don't occur individually but always in groups, with highly similar chemistries. Separating them requires complicated techniques, large quantities of chemicals, and plenty of energy before you get the pure element or metal. In Bremen, Germany, rare earth supplies are already tight and expensive. Global consumption has doubled over the past 2 decades and continues to climb sharply. Accordingly, scientists worldwide are exploring new deposits. Andrea Koshinsky of the Institute of Geochemistry investigates rare earth sources in the Pacific Ocean. She's especially intrigued by manganese nodules rich in various raw materials. Many land-based deposits lie in remote, sensitive habitats, rainforests or coastal zones, or are located in regions with deplorable working conditions. These problems might be avoided by mining in the deep sea. Hawaii. Research ships and manganese nodules. In Honolulu's port, a research vessel set sail, carrying scientists searching for rare earths. For some time, experts have known that nodules and crusts on the seabed hold elevated concentrations of nickel, cobalt, and zinc. But with new technologies like green energy, the rising demand for rare earths makes these deposits especially valuable. Since 2006, the German Federal Institute for Geosciences and Natural Resources has examined 2 sites in the Pacific. Cameras relay images of the ocean floor. But is harvesting these nodules actually easy? Environmentalists worry about the impacts of scouring the seafloor. Life in the deep sea grows and regenerates slowly, so any disruption could take ages to heal. Still, scientists hope to find millions of tons of rare earths in the Pacific, enough to free global markets from China's stranglehold. But so far, it's early-stage research. Should commercial extraction begin, we face the challenge of removing the valuable metals, rare earths included, from these nodules. Back in the lab, Koshinsky investigates the internal composition of these round lumps, which developed over millions of years around a small core, maybe a fish tooth or rock fragment, lying in sediment 4,000 or 5,000 meters underwater. Manganese and iron oxides gradually accumulated, layer after layer. Inside this unassuming black mass, rare earths crucial for tomorrow's green technologies remain hidden. Yet is it morally acceptable to exploit the ocean for electric cars, solar panels, and wind turbines? Could our supposedly green future come at the cost of destroying pristine marine ecosystems? Some argue that emerging nations need modern infrastructure, requiring robust sources of rare earths to build wind and solar capacity. The real problem is finding suitable deposits. Metals like iron, chromium, zinc, or copper appear in well-defined mineral bodies. Rare earths don't follow the same pattern. Saxony, Germany. Unexpected discoveries. In a Saxon cornfield, geologists follow a promising lead. During the GDR era, they searched for uranium but found rare earths instead. Nobody cared about these odd elements back then, so the mine shut down. Now a private firm is drilling test holes again, hoping to confirm Europe's largest rare earth deposit. However, prospective investors balk at old socialist-era data. The company must verify everything by drilling deep into the rock, believed to hold 4.4 million tons of ore, a boon for Germany's high-tech sector, which relies entirely on foreign imports for rare earth metals. A massive open-pit mine in the middle of Germany is unthinkable. The deposit here is roughly 130 meters wide and extends 1,000 meters below ground, an enormous cavern if excavated. The solution? A technically challenging, expensive underground mine. But can such a venture make economic sense? Geochemical analysis will reveal whether the deposit contains sufficient metal concentrations. Rare earths are invisible to the naked eye, in contrast to the shine of gold or diamonds. These rocks look like cement, no sparkle. However, lab tests confirm their presence. Neodymium, for example, strengthens magnets. Europium gives computer screens vibrant colors. Lanthanum improves electric car batteries. But for generations, no one knew how to use these curiously named metals. Cerium was discovered in 1803, yet it took over a century before an inventor found a bright idea for it. Early uses centered on lighter flints and gas lamp mantles. Later, people realized that lanthanum improved gasoline production. Without these contributions, gasoline might cost 10% to 30% more than it already does. Mountain Pass, California. A once prominent mine. Long before China's dominance, the United States led in rare earth production. You can find rare earths almost anywhere in small traces, but not at enough concentration to extract profitably. Mountain Pass, discovered around 1949, held substantial ore. From 1965 to 1995, it was the world's main rare earth source, producing metals for lighter flints, gas lamps, color TVs, and gasoline. Yet the ore was entangled with radioactive elements, and refining required acids like sulfuric, nitric, and hydrochloric, yielding toxic, radioactive waste. The region's geology involved multiple volcanic intrusions of carbonatite, piling layer upon layer. After a disastrous 1998 spill of over 1 billion liters of radioactive wastewater, environmental regulations forced Mountain Pass to shut in 2002. Ironically, that same period saw a tech boom. Smartphones, flat screens, hybrid cars, and green power all soared, raising demand for rare earths. We now have 7 billion people. In 4 decades, we'll add another 2 or 3 billion. They need resources, food, water, but also rare earth metals for phones, vehicles, and wind farms. Beijing's boom and China's monopoly. While the U.S. stepped back, China took over, exporting raw materials and finished goods at throwaway prices. As China urbanized, domestic consumption of electronics skyrocketed, along with the production of rare earths for items like smartphones and screens. One by one, mines elsewhere closed, unable to compete, until the world was essentially reliant on China. Over the past 10 to 15 years, China also expanded from mining into separation and refining. Now, 97% of rare earth metals come from China, giving it a dominant global stance. Then in 2011, Beijing restricted rare earth exports, and production dropped. Suddenly, the global market realized China's power as prices spiked. Energy-saving light bulbs, for instance, jumped by 25%. Officially, the reasons varied. Environmental concerns, a booming domestic market, and China's desire to manufacture finished products at home rather than export raw oxides. Some experts see it as an environmental clampdown. Others see China flexing market muscle. Mining alone isn't where the big profits lie. Processing them is even more lucrative, requiring high-tech methods. At the moment, Japan, Europe, and the U.S. do that, yet many suspect China wants to control refining too, which would let it corner the global market. With labor costs in China so low and mining relatively cheap, the rest of the world is now dangerously dependent. Entire industries can't operate without rare earths. Without them, literally, our lights would go out. In response, the U.S., Europe, and Japan filed WTO complaints against China and scrambled to locate new deposits. Meanwhile, it makes perfect strategic sense for countries to preserve their domestic reserves, just as the U.S. keeps some oil fields untapped while buying cheaper foreign oil. Bergisch Gladbach, Germany, a struggle for magnets. China's tightened export policy hits businesses that use large amounts of rare earths every day, such as magnet manufacturers like Max Behrmann. The company founder invented the magnetic fridge door. Nowadays, the firm mostly supplies the automotive sector, producing more than 50 magnet types, about 100 million magnets per year, totaling 1,000 tons, 50 of which are rare earths. Modern high-performance magnets typically contain neodymium and dysprosium, making them stronger and longer-lasting for sensors and steering systems, ensuring a comfortable driving experience. However, China's new export quotas caused a price spike for neodymium oxide, triple or quadruple within a few months, forcing production halts and late deliveries. The crisis severely impacted the company, and other sectors suffered the same fate. The entire North American and European industrial base dependent on rare earths found itself facing high material costs and a single dominant supplier. Chemist Wolfram Palitz's recycling quest. In idyllic Saxony, an inventor wants to help the tech industry. Wolfram Palitz is developing a method to extract rare earths from industrial waste, venturing into uncharted territory. Here's a tray of scrap from permanent magnet production. Material containing iron, neodymium, dysprosium, and praseodymium. Palitz aims to isolate every valuable component. Currently, existing recycling systems often target just one material, like gold, while discarding the rest. But Palitz hopes to replace destructive primary mining with clean recycling, though at present the technologies remain in their infancy and don't work for every element. He focuses on neodymium. Heating the waste in a blast furnace is the first step. Then, in a rotary evaporator, the compound changes color from pink to blue. The method functions in the lab, but the question is whether it can be scaled up cost-effectively. It's promising at a time when electric vehicles reliant on rare earth magnets herald the future. Yet EV motors generate significant heat, needing special magnets with dysprosium for thermal resistance. Dysprosium is expensive and polluting, so automakers would prefer alternatives. Ames, Iowa, rethinking electric motors. In the small university town of Ames, Bill McCallum tackles this problem, funded in part by the U.S. government. He and his team study new magnetic alloys under an electron microscope. Standard magnets for large-scale applications like cars and wind turbines need dysprosium, a heavy rare earth, far rarer than light rare earths. Although it's only about 2% of total rare earths in Earth's crust, modern EV magnets may contain up to 8% by weight, clearly unsustainable. So, the Ames scientists are devising new compounds that reduce or eliminate dysprosium, possibly substituting cerium, which is abundant, though cerium alone isn't a strong magnet. The process starts by heating the blend, then rapidly cooling it on a spinning wheel under vacuum. This yields ultra-thin metal strips with minimal dysprosium. Ideally, the dysprosium would only appear
rather than weigh the magnet core. Achieving a perfect magnet is difficult and costly, but the U.S. government's support proves the strategic value of such research.
At Tesla's factory, electric sports cars run on motors that require no rare earth magnets, relying instead on induction designs. Other automakers are following suit. If the magnet's cost hits a tipping point, manufacturers will pivot to alternative tech. Indeed, a major global automaker recently partnered with a small Californian firm to eliminate rare earths from all electric vehicles, even budget models. Wind turbines and an expanding market. Wind turbines proliferate worldwide, projected to supply 6% of global electricity by 2020, equivalent to 130 nuclear reactors. Offshore turbines are especially powerful and low maintenance, but rely on giant magnets laden with rare earths. Are we solving one environmental issue by creating another? Rare earths are crucial for clean energy, but are themselves non-renewable resources. A 5-megawatt turbine might contain a ton of neodymium, dysprosium, and other rare earths. In China, the largest growing wind market, some models need as much as 4 tons per turbine. Scientists at the Fraunhofer Institute for Silicate Research in Würzburg view today's technology as tomorrow's raw material stockpiles. Computers, phones, wind turbines, and EVs are future urban mines. Yet currently, rare earth recycling barely exists because these metals appear only in minute amounts across myriad components. Recycling mostly focuses on standard materials like copper. Rare earths demand a new level of technical and economic feasibility. Another problem, device manufacturers themselves might not know precisely what metals are present, since parts come from multiple suppliers. So a first step is building a materials database for consumer products. Once engineers know what's where, they can design strategies to disassemble devices, concentrate certain metals, and make recycling financially viable. Under a microscope, even a discarded phone can show valuable neodymium or dysprosium hotspots. But we're still far from a full-scale recycling economy. European nations see promise in recycling. Their industries need these raw materials, but the continent lacks natural reserves. Europe, however, has proven skill in developing recycling infrastructure. Researchers plan to recover more than just rare earths, copper, aluminum, even landfill mining. Realizing that the waste we discard is brimming with valuable resources, citizens must also learn to see products like phones as urban mines, not mere trash. At present, it's uneconomical to extract microscopic amounts from a mountain of e-waste. But as prices climb, new technologies will eventually become profitable. Mountain Pass reopens and future hopes. In the United States, the Mountain Pass mine has been revived amid higher world prices and a drive for independence from China. The aim is to claim 15–20% of the market with stable prices and eco-conscious processing. The company vows to avoid the dangerous acid techniques often used in China, in which radioactive thorium dissolves, polluting groundwater. Instead, they keep thorium insoluble, separating out the rare earths with minimal toxicity. Rare earth extraction remains challenging and fraught with environmental concerns, but many believe solutions are possible. Companies worldwide chase innovation, promising more sustainable, efficient processes. Yet skeptics wonder if piling rare earth metals into EVs and wind turbines actually creates new environmental burdens, defeating the green objectives. For now, the benefits of cleaner energy outweigh the negatives, but we must remain vigilant about potential harm. Resources are dwindling, so we need to adopt a circular materials economy. Only then can we harness rare earth's advantages without undercutting the environment we aim to protect. Politicians, industry representatives, and EU officials are now listening. 2 or 3 years ago, anyone who warned of a looming commodity crisis might have been dismissed. Today, everyone's talking about it, and specifically about the vital role of rare earth metals. Just as we've begun embracing more sustainable food production, so too must we revolutionize our approach to raw materials.